For coming. Thanks for inviting me. My name is Serban Constantinescu. I work for ARM, and I thought of coming over and presenting to you some of the things that I've been doing for ARM since I finished my master's at Bristol. So just to tell you a bit about myself, I have a bachelor in electronics, as a matter of fact in microelectronics, from the Constantinescu University of Bucharest. I know some of you guys are Romanians here, so probably that actually means something to you. Otherwise, it's just another electronics university in Bucharest. And I have a master in advanced microelectronics system engineering from Bristol University. And ever since I've graduated, I worked for ARM. And for the past year, I worked for ARM and Linaro. And I'll tell you a bit about what Linaro does. Linaro is basically a company that's really close to ARM. It's open source. It's a company that does open source software, and it aims to get together all the ARM partners. As you might know, ARM does CPUs, but there are actually many vendors out there which implement ARM's designs, or as a matter of fact, they design some of their own. So I'll tell you a bit about the things that I have been working on over the past 4.5 years. Mostly, I'm going to relate to Android because I work quite a bit on Android. Now today, I look after the team that develops the Android runtime together with Google as a technical lead. And I also look after the team that interacts with Bristol University. So the team that organizes all sorts of events together with Ed and other parties in Bristol University. So I'll tell you about Android on 64-bit kernels, give you a gist of how that works and what were the things that I had to fix. That's actually one of my first tasks at ARM. Then I'll tell you a bit about the 64-bit kernel ABI. I'll tell you about Android's libc, that's Bionic, and then I'll finish off with telling you a bit about the Android virtual machine. I don't expect you guys to have full knowledge of how Android works when you leave this room, but I hope to give you at least an insight on some of the things that I found useful. I try to pick up from all my years at ARM the things that kind of tricked me and the things that I had to learn along the way. And then I'll tell you a bit at the end of some other things that I think were useful over these past 4 years. So I'll be referring in the next slides to several things, several ARM-related things as AR32 and AR64. So what are those? When I started working for ARM, ARM was coming up with a specification for the ARM-V8. That's the first 64-bit implementation of ARM CPU. It's basically ARM-V8 is ARM's 64-bit architecture. It has two execution states. One is AR32 and the other one is AR64. So the 32-bit execution state basically executes the same instructions that older phones used to use. So 32-bit Android is basically running in the AR32 execution state. And then newer phones will probably use the AR64 execution state. Just to complicate it a bit more, ARM64 is the way that the 64-bit port of Android for ARM is referred, and also how the Linux kernel refers to the AR64 execution state for ARM. So Android on 64-bit kernels. This was one of the first tasks I've been given as a graduate software engineer back then. My task was basically to get Android working. At that time, Android Ice Cream Sandwich was the Android release, and to basically implement this without any user space changes. Why is that? Because I wanted this guy to keep on working. This is the Angry Birds logo, which you're probably very familiar with. So I'll be giving a Linux kernel that worked and that booted Debian and OpenEmbedded. They're both Linux distros. But that was not enough. Android needed some more things, and in particular HMEM and Binder. I just list HMEM and Binder here because they're the core things that make Android different than your Linux distro. And I'll tell you in the next slide what these guys do. You can see that I highlighted booting Linux. Maybe at some point you'll have to port Android to some new platform. The first thing that you should make sure of is that your platform boots Linux. If your platform doesn't boot Linux, then it's a no start. So HMEM is Android's shared memory subsystem. It's similar to POSIX SHM. You might be familiar with this. This is what Ubuntu uses, for example. And it has a special quality. It can discard memory when under memory pressure. So for example, when your phone hits a limit, then the applications that you have in the background might be killed because the system reclaims memory. Binary is the IPC mechanism in Android that stands for Inter-Procedure Call Mechanism. It's basically what Android is built around. So whenever your Facebook application connects to, let's say, your photos, and you share a photo on your Facebook wall, it actually uses binary. And everything else where you have an application working with another one, even as a matter of fact, the system just displaying things on the screen, they will probably go through binary. And that's a quote from one of the designers, the core designers of binary. It's basically used everywhere in Android. So, as I said at the beginning, I tried to pick up simple examples that I could relate to, and I could show you some of the work that I've done. So, I don't know if you guys are familiar with IOCTL. Does everybody here know what IOCTL call is? Okay. So, how does the user space work with the kernel? So you have the kernel, and then you have the user space. And whenever you want to do something fancy, you basically need to go to the kernel, request a special thing, and then come back. In this case, you're basically setting the size of a shared memory page or area. So you have the user space that does the things that you see above the line, and then you have the kernel that does the things below the line. And here I try to simplify the code a bit. So what I would expect in the user space would be a return of 0. But actually I get E-no-TTI. So why is that? That's because the user space is 32-bit and the kernel is 64-bit. As I said at the beginning, my first task was to get 32-bit Android working on a 64-bit kernel. So there's a big difference here. You can see that I highlighted size t. That's dependent on the compiler that you use. A 32-bit compiler would interpret size t as a 32-bit value, while a 64-bit compiler would interpret size t as a 64-bit value. So therefore, those two things, HMEM, set size, are not the same between a 32-bit environment and a 64-bit environment. So basically, the kernel provides these really nice structures. They're called compact structure. They basically make a 32-bit process work on a 64-bit kernel. And that's pretty much what I had to do at the beginning, besides some other more complicated things. But that's pretty much what I had to learn for my first days of time. The size actually matters when you do these things. So going onwards, the next task was to take a look at how we could get Android 64-bit kernel API going, and how we can basically set the steps for having a full 64-bit user space. So this is a cross-section of how Android works. You basically have the Java API. Most of the Android applications are Java-based. Then you have the system libraries, and then as I mentioned, everything kind of revolves around binary. So you have libbinary, which is a user space abstraction, also called hardware abstraction level, so you refer to it as a HAL, and then you have the service manager and the binary wrapper. So what did I want to do? I want to have 32-bit processes communicating with 64-bit processes. So I would want both of those guys to understand the same bitness, the same structures, and to interpret the data in the same way. So I picked up an example on some of the things that I had to change. And again, it revolves around setting the sizes and making sure that the size that you have, it's actually explicitly set. And you don't get beaten by the kernel or by the compiler compiling these to a different size. So you can see there that I use explicit size instead of having unsigned long, which could be 32-bit in a 32-bit environment and a 64-bit in a 64-bit environment. We prefer these sizes that basically specify how many bits we should be representing for that particular thing. So this is actually nowadays a popular interview question as well. So those two things look the same. I specify the sizes, I specify everything, but actually if I run size off on them, they're different. That's because the compiler, by default, would try to align things to what the CPU understands natively. So in this case, there would be a hidden UE32 inserted in between handle and cookie. So how could I fix that? How could I make sure that these structures are actually the same? So most of the compilers provide these packed structures and attributes. You have all sorts of attributes coming with CLang, with GCC. Some of them are standardized, some of them aren't. But this is basically how you could make sure that those two guys are exactly the same thing. So soon after I finished with these things, I posted my first patches to LKML. Do you guys know what's LKML? No. LKML is the way that the Linux kernel is developed. So the Linux kernel works by mailing lists. You basically submit your patches to a mailing list, and then probably Linus Torvalds or one of his key maintainers would come and shoot you down. So I did that. I posted my first patches on LKML, and actually I had lots of things to learn from this because my patches at the beginning weren't actually working on all the architectures, and there were particular corner cases that I didn't think of at the beginning. Plus, they were all into one patch, as I used to do when I was a student. So it was a great learning exercise, and as a matter of fact, I'm good friends with the guys that actually reviewed and merged my patches afterwards. So next I'll move on to Bionic. Bionic is Android libc. Do you guys know what you would use libc in C for? So before I libc, I'll tell you a bit about ARM64 and its register banks. So I could give you a brief overview about how Android works, but also a brief overview about ARM v8. You're probably fairly familiar with ARM, but probably not that much with ARM v8. So the AR64 execution side, that's the side that interprets 64-bit instructions, has two register banks. The general purpose register bank, that's where your int, longs, chars, booleans live. And then the floating point register bank, that's where you have your double, float, and so on. So you could see there that there are special registers for special sort of things. So for example, if I would call Ed, I would be the caller and Ed would be the callee. So my responsibility would be, if I have live values in those registers, to save the caller ones, whereas Ed will save the callee registers if he uses them. So I presented a bit on that because I'll be mentioning those registers in the following slides. So Bionic is Android's libc, libm, and linker implementation. It's BSD derivation, similar to what BSD does as a standard C library. It's not entirely POSIX compliant. So POSIX is basically a standard for the Unix operating systems that basically enables the same application you have on your Linux laptop to work on your Mac laptop. It has a custom linking mechanism and a custom thread local storage handling. This is mostly to speed up things in Android. So when you draw to the screen, you actually use some of these specialized thread local storage handling. And it has support, today it has support for 64-bit and 32-bit architectures. So here's an example. I do printf. You probably all know printf. It's the one that you write in your Hello World C example. You do printf hello world. So this is how Bionic does the printf system call. And you basically have the wrapper against vprintf, and vprintf actually does all the job for you. And let's now consider that that's a direct system call. I mentioned before that the system calls are like those I/O tools. Basically, from the user space, you go to the kernel, you ask the kernel to do something. In this case, we basically ask the kernel to print stuff to standard out. and then we return once we've done that. So the sys calls, the ARM64 system calls, they use a canonical syscall set that basically means a restricted syscall set. There are all sorts of computer architectures out there. Most of them support Linux, and most of them have all sorts of syscalls which could do the same thing. I give you an example here with syscall app, for example. One uses the relative path, one uses the absolute path. If you have the absolute path, the one that does the absolute path, then you can also do the one that has the relative path. There's no need for it. So arguments get passed in x0 to x7, and that comes back to the previous slide where I showed you the register banks. And then the syscall number gets passed in x8. And then besides these things, I also worked on multiple other fixes for 64-bit linking and some handling for the thread local storage. Here's an example that I'm going to take on to some of the lib work I've done. So this is basically a simple example where I just do scene of 0, and I want to see what's the value. I basically return the value of scene. So in general, computer architectures have two ways of passing arguments, register-based computer architectures. They have a soft float ABI, which basically your ARM phone, your 32-bit phone will use. That means it would pass the floating point argument in the integer registers, in this case in R0. Or they have hard float ABI, which means they will pass the floating point values in floating point registers. So ARM64 is always hard float. Whenever you have a rich operating system on top of an ARM v8 CPU, and if you execute the AR64 execution state, you will be passing float and double arguments like this. For a 32-bit ARM CPU, and as a matter of fact, in the Android context, you will probably be passing the registers in the integer, the values in the integer registers. So, as I mentioned, ARM64 is always hard float. We always pass arguments in the floating point registers, and we have separate registers for the control. We have separate floating point control and status registers. This is a comparison to ARM, which I expect some of you will be familiar with. And those are the speedups measured probably a year and a bit ago, and a comparison between AR64 and AR32 for particular event functions. So, at some point, we started upstreaming this work, the work that me and some of my colleagues have been working on. I worked quite a bit on Bionic. I still try to fix things from time to time when I have the opportunity. We upstreamed almost 10,000 lines. That's support for ARM64 in particular. And we had, in general, a good speed up compared to 32-bit. So I'll move on to the Android virtual machine. I've been working on this for the past 2 years and a bit. It's probably the core of Android. And why is that? Because all your applications are Java, and they need to run on a virtual machine. So I'll be presenting you what the Android virtual machine does. So you often hear in the Android context, you often hear people referring to the Android virtual machine as a Dalvik virtual machine. But why isn't it a Java virtual machine? Because my code is Java. So this is the Java source, just a simple example. It could also be Angry Birds written completely in Java. And those are two bytecode implementations. One is the Java bytecode, which is stack-based. I'll tell you a bit about it in the next slides. And the other one is Android's own representation, which is the Dalvik bytecode. And you can see there how Dalvik and Java interpret the code, the Java code, on your right-hand side, left-hand side. So Dalvik is, as I mentioned, is Android's virtual machine implementation. It basically pretty much mirrors what the Java implementation does, with big difference. The big difference is that it's a register-based virtual machine compared to a stack-based virtual machine. You could see in the previous slide that basically what we do here, we add things to the stack, and then we load things to the stack, and then the multiplication or whatever operations we do are done on the last two operands in the stack. Whereas the other one, the Dalvik bytecode, is register-based. We operate on virtual registers. So they're pretty much the same, with the addition that Dalvik is basically compacted. It's a set of compacted classes. So we have untyped constants, untyped array operations, whereas Java is more consistent when it comes to typing. So whenever you do, let's say, whenever you have an array of doubles, that would be a different operation than when you do operations on an array of longs, let's say. So the Dalvik virtual machine, the virtual machine that we refer to in the Android context, it basically mirrors common architectures, modern architectures. It has 2 to the power 16 virtual registers, which are 32-bit. It has different type of operations that operate either on the first 16, 256, or all the virtual registers. It follows the Java memory model, and it has its own bytecode specifications. The implementations for the Dalvik virtual machine are ART and Dalvik. So here's an example of an operation. It's actually copied from the previous slides. So this is an example bytecode where move basically specifies the base operand. That's the operation that we want to do. Then it handles 64-bit data, so it needs to be a move Y. It moves things from high register. So that's what a from does. It's an operation opcodes suffix. And then you obviously have the destination and the source register. So we go from Java to Dalvik to ARM64 generated code. So how, in the next slides, I'll tell you more about this side here, how we generate the ARM64 code. So we generate it in 2 ways. We generate it with a virtual machine. Here I'm giving you a comparison between Dalvik, which used to be the default Android virtual machine until Android L came out, and then from Android L onwards, ART is the default virtual machine. So they're both of them are Dalvik virtual machine implementations. Dalvik has an interpreter, a fast interpreter, and a tracing JIT. Whereas ART has interpreter, AOT compiler, and more recently, it also has a JIT. But ART, besides all the other things that it does, it also has a more pluggable and parallel garbage collection. The garbage collection is the one that has to do, most of the times, with the slickness that you see in your Android phone. When garbage collection happens, the usual model is stop the wall, garbage collect, and then come back. So that means that you start taking a look through your Facebook, and then at some point your application basically freezes for less than a second most of the times. But that's basically something that Google calls junk. So the main key is to get as interactive as possible and to stop the world as few times as possible. So ART, which as I mentioned before is the default Android virtual machine since Android L, it has a ahead of time compilation, so that means you compile code before you execute it, and also has a just-in-time compilation, which basically means that you compile code as you execute it. I mentioned there that the just-in-time compilation is part of what happens now in Android Master. And it has a new compiler backend. That's the optimizer compiler. That's what me and my colleagues are working on. And obviously it has a few other distinctions when compared to Dalvik. So here's a compilation overview of how your application gets compiled. This relates to Android M and Android L. So you basically have your Java source code that you compile to Java classes and then DEX classes using the old compilation method that's using Jack and DX. Basically, after compiling it with Jack, you could with Java-C, sorry. After compiling it with Java-C, you could run it on your Linux or Windows host. And then new compilation, which basically gets straight from Java source files to DEX classes using Jack. Then everything gets packaged up in the APK. That's together with your photos and whatever else your application needs, and gets transferred to the target. So all of that happens on the host side, so on your development platform, the one that you write your applications on, most probably your laptop. And then this is what happens on the target side. So Dextoad gets invoked. Dextoad basically invokes the compiler, the optimizing compiler in this case, and that basically generates ELF files. So this is what I've been focusing on for the past year and a bit, maybe a year and a half. It's called the optimizing compiler. It's the compiler that comes with Art. Basically, this compiles your DEX classes to the native code. It has a single level IR. IR stands for intermediate representation. Usually your compiler basically speaks and generates code based on the intermediate representation. It has a register allocator which is independent of code generation. That's a key attribute because in general compilers are, the register allocator is quite tied into how the compiler works and it's not too flammable. Whereas in the case of the optimizing compiler, you could slot in another register allocator. And for ARM64 we use Pixel for code generation. So here's a brief overview about how the optimizing compiler works. So we had the DEX bytecode as input, and in the first stage we basically generate the intermediate representation graph. We go through every single bytecode in the DEX bytecode that we have provided as the input, and we generate the basic blocks. Basic blocks is again compiler terminology. It's a portion of straight line code without no branches in or out of. So whenever you have a branch, let's say a system call or any other type of code, that would be a point where you split up into two basic blocks. And we generate the HIR. HIR stands for high level IR for all those bytecodes. Either one, either more than one HIR. And then we iterate over the HIR graph. We apply different passes. Here I gave you an example of some of the optimizations we currently do. There are obviously many more than this. But we apply on the HIR all sorts of optimizations. A simple one that I could tell you quickly how it works is the instruction simplifier. So for example, when you do AND with 0, the result will always be 0. So what's the point of doing the AND operation? You could just use 0 as a result. So that's one of the things that the instruction simplifier does. The other things do probably more interesting things, but they're too complicated to explain in just a few words. So once we have applied all the optimization passes, we go ahead and we allocate the registers. We do the SSA liveness analysis. That's static single assignment. Again, some compiler terminology. And we compute the locations that we would need for the code that we're just about to generate. Once that's done, we generate the frame entry, frame exit, and we go ahead and generate code. For ARM64, we use Pixel, which is an open source project that you guys could contribute to. And that's pretty much what I had to talk to you about. I hope I haven't lost you all along the way. Again, I was just hoping to put together some slides just to tell you a bit about some of the stuff that I've been doing for ARM. Hopefully that got you interested in what we're doing at ARM. I have here a slide which seems to be pretty up to date. These are our latest vacancies, so you guys could go ahead and check them out on the ARM website and apply for them. And hopefully we have some time for you guys to ask me questions about whatever you guys would like to ask me. It could be either technical on the optimizing compiler or any of the things that I presented on, or on just how it is to be a software engineer. Yeah, go ahead.
What kind of things will you be doing as a software engineer?
So, I work in systems and software. That's basically the division that does operating systems in ARM. I work in the open source side of SSG. So as a software intern, you could either work in SSG and work on open source operating systems. Either work in MPG, which is the graphics division. That's where you would do the things that are slightly more related to the graphics side. Or you could work in another division that does the CLang and GCC compiler. They're all pretty interesting things. Some of them are low-level software, like I do, like mostly around kernel, user space interaction, C, C++, sometimes C++ 11 and 14. That's actually what we develop our team. But they could also be a bit more high level in the graphics division, like building apps and this sort of thing.
Do you want to work closely with app developers to help them optimize how they use things like the virtual machines? So when Angry Birds is a very popular one, do you work with Angry Birds to help them optimize their code?
So we do interact with some application developers. We try as much as we can to document all the things that we suggest as good practices. So everything should be up there and should be easy to get to. And obviously, if you have any sort of questions, then ARM is willing to help. So, yeah. Any other questions? I've got some questions for myself. I thought about it on the way here. What I would have liked to find out is go ahead.
I was going to say, there was one other. You said that it has its own bytecode for the Dalvik virtual machine as opposed to the standard Java one. Is that an open bytecode? Can you look up the standard for that? Or is
Yes, yeah. So all the things that I mentioned in all the slides are open source projects that you guys can contribute to. You can see, if you Google what I've done, you can see the things that I've started off with. So yes, everything is public, documented to some degree, but yeah, there are always people willing to help when documentation is lacking. Any other questions before I ask myself questions?
Well, as you've got vacancies on the board, what's it like to work at ARM? Is it nice? Do they have free cakes? I mean, will our students like it?
Yeah, we do have free cakes from time to time. So that's a plus. It's always a plus.
And it was a nice campus. It was a nice.
Yes, yeah.
Physically nice, right? It's outside Cambridge?
It's actually in Cambridge. It's just on the outskirts of Cambridge. So yeah, how is it to work for ARM? So I work for ARM in Cambridge and Lund. That's in Sweden. So I went there for 6 months, sort of rotation. It was an interesting experience in Lund. Back then they had a really small office in the city center. Lund is pretty much like Cambridge. It's a student city. So they had an office in the city center, which was pretty nice because I was going and grabbing lunch at a restaurant in the city center. The Cambridge side is way bigger than the Lund side. We have our own big fancy canteen. And as a matter of fact, ARM is actually building 2 huge new buildings that are hopefully going to accommodate us soon. I think ARM is pretty cool to work at, mostly because it's still a small company when compared to Intel. We're probably at least the order of magnitude smaller. So you always get to interact with the people that actually get to do the stuff. So when I started working at ARM, I had support from the guys that do the GCC compiler and the guys that do the Linux kernel, and actually we had to clarify some of the specifications of ARMv8, which was pretty interesting. There were corner cases that I didn't spot, but we did because we were doing the user space. And it's nice because you get to interact and to find out things from actually the guys that get to do them, from the hardware engineers and the guys that design the CPUs. So it's pretty nice from that aspect.
So you said that you're working a lot with other teams. What's a typical team size then?
It depends a lot, from division to division, from project to project. It depends a lot. It can be from one guy to, I don't know, probably 50 or so for a big CPU project. The team that I'm working was at the beginning, was started off maybe 2 people, me and my tech lead back then, and now we're probably around 10 people. And we probably had a peak when we were doing the Android 64 board, about 15 people, something like that. But then it depends a lot from team to team. Yeah, go ahead.
So if ARM have done 64-bit now, and obviously there's still more software development to make every app 64-bit on, but on an architecture side, where's it headed?
So I think there are many other things coming soon. Some of them are public, some of them are not. But there are always architecture developments. 64-bit was indeed a big change, but up to then, ARM has always been a 32-bit architecture. And by the point we switched over to a 64-bit architecture, we were already up to the 7th iteration of the architecture. So there are new things coming along, new instructions, support for all sorts of things. The software world evolves, the architecture needs to evolve, so that's always going to happen.
So if you're adding more instructions and developing things like that, and obviously ARM has added more and more instructions over time, is it not gradually straying from its original RISC kind of basis?
I guess the answer would be that as a concept, ARM is still a RISC architecture. We don't do things like Intel, like for example, the CISC architecture we do when we do addition of the memory or stuff like that. We're still a register-based RISC architecture. There are more instructions to be added, but not instructions that do complex stuff with memory or any other subsystems. They do complex stuff on the registers. So, yeah. Okay. Back to my questions. I still have like 10 minutes probably. So I thought on the way here, what did I find actually interesting, and what would have I liked to find out before starting to work for ARM? So I think, first of all, at the beginning when I started working for ARM, I was under the impression that Android is actually done just by Google and nobody contributes to. As for many other things, like Canonical does Ubuntu and that's it, nobody else helps. Actually, all the open source projects have contributions for all sorts of companies, all sorts of interesting people that you get to work with. Working in open source also means that from time to time you get to meet these guys, you get to attend conferences and get to work with guys that actually might be the absolute expert in what you're doing. So that's pretty interesting. That's a good opportunity if you're working in such an environment to attend some of these things and to get to speak with interesting people. So following up from this, one of the graduates that started a couple of last year actually, Pierre, has worked in our team for a while. So ARM has this concept of graduate rotations, so you move from one team to another for a period of 3 months. So that means you have 4 rotations over a year. So one of the guys that worked in our team, actually a couple of months after he joined, he did an awesome job on one of the projects that we were working on. And he had the opportunity to speak about the work that he has done in Seattle at a very big Linux conference. It's called Linux Plumbers. As a matter of fact, he had the opportunity of seeing the Linux Torvalds live next to him. So that's pretty cool stuff that I don't think you get to do if you don't work in an open source environment. And then
it's probably about time.
yeah. And then that's pretty much it. If you guys have any other questions, just follow up with me. You have my email, probably you have my contacts, or you can follow up through that. Thanks a lot. Thanks a lot.
Thank you guys. Do come and ask questions if you have them. Or email me through treasurer@BEEES.co.uk if you want to follow up.